Good day, students. Welcome to part one on rectangular approximations, or you can also call it the Riemann rectangular approximations. We're going to be looking at how to approximate areas using the left endpoint, the right endpoint, and the midpoint rectangular approximations, all right? So before we go ahead and look at the example, let's take a look at the formulas. All right, so the formula is as follows. Let's write this down. Formulas. So to approximate, approximate the area under a function f of x, under f of x, from x sub 1 to x sub n, which is an interval on the x-axis, okay? Now, the area under a function from x to x sub 1 to x sub n can be written using the tool of calculus as the definite integral from the lower bound x sub 1 to the upper bound x sub n of the function dx. Okay, so this is the same thing as the area under the function f of x from x sub 1 to x sub n. Okay, all right. Now, how can we approximate this? Well, this can be approximated with n equal subintervals using the left-hand rectangular approximation LRAM. You can use the left endpoints to do the approximation. If you want to do the LRAM, that is equal to h times f of x1 plus f of x2 plus f of x sub n minus 1. Okay? Now what we're doing is we're calculating the area of n rectangles. Okay? So h represents the height, h represents the width of the rectangle, and f of x sub 1, f of x sub 2 represents the height. Okay? Now, since we have uniform widths given by h, then we can factor out all the uniform widths from all the heights. Okay? So just factor them out. And then we have this formula right here. All right? One thing to note is that when you're doing your left-hand rectangular approximation, you take all the points on the interval to the left of your right endpoint. So the right endpoint is x of n, so all the calibrated points to the left of that, starting from x sub 1, will be used in computing your left-hand rectangular approximation. That's why we have x sub n minus 1 as the last height. Okay? Now, how about if we wanted to compute the right hand or right endpoint rectangular approximation? If we want to compute this, it's similar to the left-hand rectangular approximation. The only difference is we're going to pick all the points to the right of the left endpoint on our interval. So we're using n equal subintervals here, so we can have h, respective widths, factored out, times f of, instead of starting from the left endpoint, we are going to skip that one. And we're going to go straight to f of x sub 2 plus f of x sub 3 plus, we go all the way to the last endpoint, okay, which is f of x sub n. So this is your right-hand rectangular approximation. Now let's look at the midpoint rectangular approximation, MRAM. The midpoint rectangular approximation is given by finding the midpoint of all the calibrations on our n sub interval. Okay, so the midpoint of x1 and x sub 2, we have f of x1 plus x2 over 2, okay, plus the next one is the midpoint between x2 and x3, so x sub 2 plus x sub 3 over 2. Follow that pattern all the way to the midpoint of the last endpoint, so your calibration, so x sub n minus 1 plus x sub n over 2. Okay, so these are the formulas. So what is h? Where h is the length of the interval, x sub n minus x sub 1, that's how long it is, and we're dividing it into n equal subintervals over n. All right, so that's what h, or the width of your rectangles, are. Okay, so these are the formulas. Let's go ahead and apply it to an example. So for example 1, we're to find the left rectangular approximation, the right rectangular approximation, and the midpoint rectangular approximation using the formulas indicated above here. Then find the exact area using geometry. Okay, remember these are not exact areas. They could turn out to be exact, but these are approximations. In some cases with certain curves, some of these approximations might turn out to be the exact approximation. In other cases it's not. Okay, so we're going to find the rectangular approximations, and then we're going to find out what the exact area is, and then we're going to see how accurate our approximations were. Some of them one of them might even turn out to be 100% accurate. Okay? So the function under consideration is f of x equals negative x plus 4 on the interval 0 to 4 using 4 subintervals. Okay? Alright, so first thing we're going to do here is we're going to find the left-hand rectangular approximation. So we want to find the area, approximate the area under the curve from 0 to 4 of this function using the left-hand rectangular approximation. So the area, which can be written using calculus notation as the integral, the definite integral from 0 to 4 of the function negative x plus 4 dx. This is the exact area. Expression for the exact area can be approximated using the left-hand LRAM as follows. So before I write down what the formula is, let me set up my interval so that it's easy for us to see what goes into my left-hand rectangular approximation. So let me do a setup right here. So I'll make up an interval from 0 to 4. So let's start from here, 0 all the way to, let's do that again. 0 all the way, 1, 2, 3, 4. So we are going from, there goes the number line from 0 to 4. So from 0 goes 0 to 4. So 0, 1, 2, 3, 4. This is nice because by just going by the units, we have 1, 2, 3, 4 subintervals, so this is perfect. If not, we just have to figure out a way to divide the whole interval into the number of subintervals that is indicated in the problem. Okay, so this is a nice problem for us. Now, we're going to label our calibration starting from the left endpoint all the way to the right endpoint. The first one is x1. This is x1. Next one is x2, x3, x4, and x5. Okay? Now, when we're looking for the left rectangular approximation or the left Riemann approximation, we're going to take all the points to the left of our right endpoint. Our right endpoint is 4, so that will be excluded from our rectangular approximation. Okay, so we're simply going to start from x1 all the way to x4. Okay, so this will give us our left endpoint rectangular approximation. All right, so let's indicate that. So from here to here are the x values that we'll use to calculate LRAM. Okay, now what if we want to look for the right endpoint rectangular approximation? All we'll do is we'll pick all the points to the right of the left endpoint. So x1, the left endpoint, will be excluded from our inputs. Okay, so we're simply going to go from x2 all the way to x5, and that will give us the x values to compute our right rectangular approximation. So this right here is RRAM. Okay, now what if we want to find the midpoint rectangular approximation? We will just have to compute the average of these calibrations right here, these points that we're going to be using. So we're going to find the midpoint of x1 and x2 graphically resides here, and the midpoint of x2 and x3 resides here, the midpoint of x3 and x4 which resides here, and the midpoint of x4 and x5 which resides here. So these green tick marks are what we're going to use to calculate our midpoint rectangular approximation. Okay, so we're going to go from here, let's do that again, from here all the way to there. Okay, and that will be our midpoint rectangular approximation. Let me put it in green. So from here to here is our midpoint rectangular approximation. Okay, so this setup right here will help me easily determine the values of x I'm going to be using to calculate my rectangular approximations. Okay, so now I'm going to apply this formula that we wrote up here and this setup I have here together and use it to find my LRAM. Okay, so we're going to have the individual heights of the rectangle. Let me change the color. Individual heights of the rectangle h times f of, we're going to go for LRAM. We're going to pick all the points to the left of x5, so x1, x2, x3, and x4. F of x1 plus f of x2 plus f of x3 plus f of x4. Okay, so that's what our LRAM is going to be. Okay, now let's go ahead and compute the area of our rectangles. Let me make a real quick change in notation here because it's a little bit confusing. Let me change my h, this h, let's call it w, okay? Just for symbolic convenience and to avoid confusion, let's call this w right here. So we'll call that width as opposed to height. And let me update these formulas. Sorry about that. So instead of calling this h, let's just call it w, okay? So the width times the height. So call this w, w, w. In some textbooks it's called h, but I think if we call it w, it makes more sense. Okay, So now, what is the W? What is the width? How wide are our intervals? From x1 to x2, how wide is it? x2 to x3, x3 to x4. We can clearly see that it's 1 unit long. Okay, that's how wide it is. And these will help us compute our the height of each rectangle. So how we know that the width is 1, but how can we compute this using a formulaic approach? W is basically the length of the interval, 4 minus 0, divided by the number of subintervals you have, which is 4. Okay, so if you want to do this without looking at this setup, you can do it arithmetically using the length of the interval divided by the number of subintervals you have. So we can see it's 4 over 4, which is 1. Okay, so we have all the ingredients we need to determine our left rectangular approximation. So LRAM is going to be the width of each rectangle. You see they're all equal widths here. So we have 1 times, let's do that again, 1 times f of, first candidate is what? Is 0, right? F of 0, because that's x1, f of 0, plus f of the next one is 1, plus f of 2, plus f of the last value for LRAM is 3. Okay? And then what are we going to do now? We're just simply going to plug all of these values into our function. Okay? So what does our function do? This is a simple function. You're just basically subtracting our inputs from 4, because this is the same thing as 4 minus x, right? So we can do this easily. So we have 1 times f of 0 is 4 minus 0. 4 minus 0 is 4. Plus f of 1, if you plug in 1 here, 4 minus 1 is 3. Plus f of 2, plug in 2 here, 4 minus 2 is 2. F of 3, plug in 3 here, 4 minus 3 is 1. Okay? And we add all these values together, 4 plus 3 plus 2 plus 1. 7 plus 3 times 1 is 10. So that's your first answer. LRAM is equal to 10. Okay, now let's look for the next one, which is the right rectangular approximation. So we have RRAM. The area can be approximated using RRAM. Let me move this back a little bit so I don't run out of space. So RRAM is equal to the width times f of x2. You notice we start from the second one, f of x2. Pick all the points to the right of the left endpoint, f of x2 plus f of x3 plus f of x4 plus f of x5. Okay, this is a right rectangular approximation. Okay, pick from here 1, 2, 3, 4 to the left of the right of the left endpoint. Okay, so we know what those values are: 1, 2, 3, and 4. So we're going to plug them in. We already know the width of our subintervals are all 1 times f of 1 plus f of 2 plus f of 3 plus f of 4. Okay? And then if we evaluate this, we have 1 times f of 1. You plug in 1 into your function. We already did that before. So that's 4 plus 3 plus 2 plus f of 4. If you plug in 4 here, 4 minus 4 is 0. Okay? And when you add all this together, 4 plus 3. Okay, I think I made a mistake here. F of 1 is, so let's fix this. Alright, so sorry about that. F of 1, f of 2. F of 1 is 3. F of 2 is 2. F of 3 is 1. Okay, perfect. So it's 3, 2, 1, 0. Alright, so if you add 3 plus 2, that's 5 plus 1, 6. 6 times 1 is 6. Alright, so that goes your right rectangular approximation. Alright, next thing we're going to do, lastly, is the midpoint rectangular approximation. Okay, so we're going to have the width times the average of our intervals here. So it's going to be f of the average of the first two intervals, x1 plus x2 over 2, plus f of the average of the next two, x2 plus x3 over 2, plus the average of the next two, f of x3 plus x4 over 2, plus the last one, f of the average of x4 plus x5 over 2. Okay, so that's what the midpoint rectangular approximation is. You're basically looking for the midpoints of the calibrations of your subintervals. Okay, so we know that the width of each interval is 1 times. Now we can just use the appearance of our graph here to determine what the midpoints are. So f of the average of 0 and 1 is 1 plus 0 over 2, which is 1/2, plus the average of 1 and 2 is 2 plus 1, 3 over 2, 3 halves. You can see a pattern here, which is the odd numbers in the numerator, plus f of average of 2 and 3 is 5 over 2, plus average of 3 and 4 is 7 over 2. Okay, so this is what you get when you do the midpoints of each interval. All right, so now we're going to plug all these into the function. So all you're doing is you're subtracting these from 4. So if you subtract 1/2, look at 4 as 8 over 2, okay? Because we know 4 over 1, if you times it by 2, top and bottom is 8 over 2. So if you subtract 1/2 from 8 over 2, you're going to have 7 over 2, plus subtract 3 over 2 from 8 over 2, you have 5 over 2, plus subtract 5 over 2 from 8 over 2, you have 3 over 2. And then the last one is 1 over 2. Okay? Now if you add this all together, your final answer is going to be 7 plus 5 plus 3 plus 1 is 16 over 2. 16 on the top over 2, which is just 8. Alright? So 8 is our midpoint rectangular approximation. Now, I'd like to represent our solution graphically for you so you can see exactly what it is we're doing. Okay, before we shift to the geometric representation of these results, let's find out what the final answer, the actual answer is, the actual area. Okay, so let's look for that. So these are approximations that we just did. So actual area is given by, using the calculus notation, the integral from 0 to 4 of the function negative x plus 4 dx. Okay, so I'm going to show you how to do this with your calculator. There are different ways you can do it with your calculator. I'll just show you 2 ways. So I'm going to be using the TI-89 titanium to show you. This syntax is similar to the standard TI-89 calculator too. Okay, so we're going to go to the calculus menu, F3. Let me make it a little bit bigger so you can see clearly. All right, so F3 gives us a bunch of calculus functions. So we want to calculate the integral, okay, the definite integral. So you select that, press enter. Now the syntax is you enter the function, the variable, your lower bound, and your upper bound. Okay, so the function is negative x plus 4. Your variable of integration is x. Your lower bound is where you're starting from, 0. And your upper bound is 4. Close your bracket, enter. Your area is 8. So the actual area is 8. Okay, let me show you another way of doing it. Another way you can do this is you go to your graphing menu. And then you enter your function, negative x plus 4. This approach is similar, it's universal. You can also use this approach for your TI-83 or TI-84 calculators too. Okay, so press enter. So what we're going to do is we're going to graph this function, and then we're going to use the math menu to calculate the area under a specified interval. Okay, so you press diamond F3 to graph. So there goes your graph. Now we're going to calculate the area from 0 to 4, the exact area. Okay, we're going to use the F5 menu, which is for math. Okay, so F5, and then we're going to go to option 7. You can see there the integral of f of x dx, which represents the area for the specified x interval. Scroll down to 7, or you can just press 7. Okay, and you press enter. It asks you for your lower limit of integration. So our lower limit we can see is 0. You press enter. It asks you for your upper limit, which is 4. Press 4, enter, and it tells you what it is. See, the area of the function from 0 to 4 is equal to 8. So that's our answer. Okay. All right, now if you look at this, we can clearly see that it turns out that the LRAM was an overestimate, the RRAM was an underestimate, but the MRAM turns out to be the exact answer. Okay, so that happens to be the case. This is not always the case. For linear functions, you have a situation like this. So the MRAM actually did an excellent job here. It was an exact answer. Okay, so now let's look at the geometric or graphical representation of all these computations we just did. Okay, so we're going to look at the graphical and geometric representation. So this, since it's a linear situation, this can actually act as a verification tool to help us verify that our answer is in fact correct. Okay, so remember the function we're dealing with is f of x equals negative x plus 4 on the interval 0 to 4. Okay, so since we have this linear function, the slope is negative 1 over 1. We're going to rise negative 1, which is a fall of 1, and run 1. And your y-intercept is 4. Okay? All right, let's start with the left rectangular approximation, LRAM. So we're going to grab this function. Let's set up our coordinate system. 1, 2, 3, 4, 5. So let that be my y-axis. 1, 2, 3, 4, 5. Okay, let that be my x-axis. This is how I'm going to calibrate it. So this is my y, my x. Let's call this 1, 2, 3, 4. We're going from 0 to 4, okay? And my y-intercept is 4, so let's call two tick marks. 1, 1, 2, 3, 4. Okay? So this is the setup I'm going to be using for my LRAM, MRAM, and the actual area. Alright, so I'm going to copy this. Hold on for a second. Okay, let's look at our LRAM. So I have the same coordinate system replicated 4 times, so I don't do the same thing over and over again. Okay, so for LRAM, we know that the y-intercept is 4, so we have a point here, and then we're going to go down 1 over 1, like that, down 1 over 1, down 1 over 1, because we have the slope of negative 1, down 1 over 1. Alright, so this is the graph of the situation that we're looking at. Draw a straight line. Okay, so there you have it. So what does a left-hand rectangular approximation look like? Well, we're going to be looking at all the points to the left of our right endpoint, which is 4. So we're going to look at this point. We'll define the first height of our rectangle. This will be the second height of the second rectangle. This will be the next height of the third rectangle. And this will be the fourth height of the fourth rectangle. We ignore this point right here. Okay? So these are the points that we're going to be using to create our rectangle. So this is how you set it up. Using this point, I will create a rectangle of width 1 unit. Remember we talked about what the width was, which was 1 unit. Okay? So there you have it. And then this is a second rectangle right here. This is f of x2, which is 1. shift to the right a little bit. And then the next one, let's see, f of x3, that's the third one. And then f of x4, that's the fourth one. Now, if you notice what's happening here, the left vertex on the top of the rectangle is what hits the curve. So that's what the left rectangular approximation is, okay? Now, what are the areas of this rectangle? It's very easy to compute. The height of this rectangle is 4 and its width is 1, so the area of this is 4. The area of this is 3 times 1, 3. The area of this is 2 times 1, 2. And this is 1 times 1, 1. So we can see that LRAM, based on this geometric representation, is 4 plus 3 plus 2 plus 1, which is what we got before, a value of 10. So we're confident that our answer is in fact correct. All right? Now, what does the RRAM look like graphically? How does that look like? How does that differ from this? Well, let's draw a graph again. We already know what the graph looks like, so I'm just going to go from 4 down to 4, like that. In this case, what we're going to do is graph the right endpoints to all points to the right of the left endpoint. We know the left. All right, so recall that this was x1, and then this is x2. So these are the points we're looking at. So this is going to be x2, x3, x4, and x5. So these are the points that determine the height of our rectangles. Okay, so let's go ahead and draw the RRAM rectangles. So this is the height of the first rectangle, and this is the height of the second rectangle. This is the height of the third rectangle, and this is the height of the fourth rectangle right here. Okay, so what do you notice here? You notice that the right vertex on the top of the rectangle is what touches the line. Okay, so that's what your right rectangular approximation is. Compared to the LRAM, it's the left vertex on the top that touches the graph. Okay, and then if we want to see what the area is here, this has a height of 3 times the width of 1, 3. This has a height of 2 times the width of 1, 2. This has a height of 1 times the width of 1, 1. This has a height of 0 times the width of 1, so area of 0. Okay, so RRAM is simply going to be the sum of these numbers, 3 plus 2 plus 1 plus 0, which is equal to 6. So we can see that our final answer, the initial answer we got, is in fact correct. Okay, all right, how about MRAM? How does that look like graphically? Midpoint rectangle approximation. Well, let's sketch the graph again. We know what it looks like from 4 all the way to 4. Now, the midpoint of the x values determine the height of our rectangle. Okay, so this time we're going to look at the midpoint between x1 and x2, which resides right here. The midpoint between x2 and x3 is right here. And then midpoint between x3 and x4, and then x4 and x5. Another way to do it is you can just draw a midpoint, a line from the midpoint where the midpoint touches the line, like that. Just go from the midpoint and just trace it up, and that defines the height. Okay? Well, it makes a triangle look messy, but that's how you figure out the height of your MRAM. Okay? I don't want to do that because I don't want to make it look messy. So just trace your midpoints all the way up. Okay, so this is the midpoint I'm looking at. Trace this up. Trace this up. Trace this up. Trace that up. And that's basically where it hits the line. Okay, so now what does the rectangle look like? You just simply draw it like this. That's the top of the rectangle down. So you notice that it's the midpoint of the top of the rectangle that touches the curve, and then the second rectangle looks like that. Let me shape that up a little bit so it looks more accurate. Shape that up a little bit. Yeah, I'm like that. Okay, and then the next rectangle looks like this. That's the third rectangle for MRAM, and then the fourth rectangle looks like this. Okay. All right, and then we already computed what the area is here. This one has a width of 1 and a height of 7/2. This has a width of 1 and a height of 5 over 2. This has a width of 1 and a height of 3 over 2. And this has a width of 1 and a height of 1 over 2. So if you add all this together, it's exactly what we had before. MRAM is going to be equal to 8. Okay? So that checks out. Now the last one is the actual area. The actual area, we use a calculator to do it, but this is an easy problem. You don't actually need calculus to do it. So an overkill, you can actually use geometry, but I wanted to show you how to do the process using a calculator. Okay, so this is the actual area. Now, how do you calculate an actual area? It's really easy, right? Think about geometry. The area of a triangle is 1/2 base times height, right? So the base of this triangle, this is the base right here. The base is 4, and the height is 4. So the area is going to be 1/2 of the base, which is 4, times the height of 4, which is equal to 8. Okay? So that's the actual area. And we can see that MRAM is an exact result for the area of the triangle. All right? So that's that. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel for other cool clips such as this. And please post a comment to let me know what you think about this presentation, and give me a thumbs up if you liked it. I appreciate it. More clips can be found on mathgotserved.com/calculus. Thanks again for watching, and have a wonderful day.